All right, so this is kind of where we left off in Chapter 4 before we went away for break. We were looking at solving differential equations using Laplace transforms. What do? How do you solve that differential equation using Laplace transforms?
You have to get the form right, so you should do like the s of x things, right? The x's.
All right, so we take the Laplace transform of the second derivative. We had a rule for the Laplace transform of the second derivative. It was s squared capital X minus s x at 0 minus x prime at 0. That was our rule for the Laplace transform of the second derivative. Plus, then we just have the Laplace transform of little x. The Laplace transform of little x is big X equals the Laplace transform of cosine t, s over, and in this case k is the number 1. So it's s over s squared plus k squared, but k is the number 1. K is the number right there. All right, well, this one's not so bad because of our initial conditions. That one's 0, that one's 0, so those fall out. Then what did you do?
Combine the big x's.
You want all the big x's on one side and all the stuff without big x's on the other side. You already have that for here. Why do you want all the big x's on one side?
So you can get that, bring the s squared.
So, well, not just the s squared, because we have two big x's. We can factor out a big X. So we factor out a big X. We're left with s squared plus 1 equals s over s squared plus 1. You divide. So big X is s over s squared plus 1 squared. Now what we wanted to do was we wanted to find the inverse Laplace transform of this function. And what did we have to do in order to find the inverse Laplace transform of that function? That's a partial fractions problem. And it's kind of an ugly partial fractions problem, isn't it? How come? Because you have a quadratic on bottom that doesn't factor s squared plus 1, and then it's squared, which means you need a repeat. So I'm not going to work out the whole problem, but what we would have had to done, we'd have to write as plus b over s squared plus 1 plus cs plus d over s squared plus 1 squared. We would have had to clear our fractions, plug in some nice numbers, hope we can make things work out, figure out A, B, C, and D, and then take the inverse Laplace transform. Kind of a real pain in the neck, actually. Today, we're going to learn a different way. Notice that this capital X is s over s squared plus 1 squared. I could write that as s over s squared plus 1 times 1 over s squared plus 1. What's interesting about that?
You don't need to do the right?
Yeah. That's called. Inverse is already in. Yeah, there's also.
What's the inverse Laplace transform of this? That's cosine t. What's the inverse Laplace transform of that? Sine t. Unfortunately, this isn't true. What I'd really like to do, I'd really like to say x of t is the inverse Laplace transform of s over s squared plus 1 times 1 over s squared plus 1. What I really wish I could do is I really wish I could say that that equals the inverse Laplace transform of s over s squared plus 1 times the inverse Laplace transform of 1 over s squared plus 1. But unfortunately, I can't do that. That's not true.
Wait, why isn't it?
Why isn't it true? That's an excellent question. Why isn't it true?
Because you're basically integrating.
Remember that Laplace transforms involve integrals. Do integrals work well with multiplication? No, not at all. That's why we have things called integration by parts. And we have trig substitution, and we have all those other things that we had to use to deal with multiplication. Doesn't quite work. But it's close. It's very close. So what we're going to do today is we're going to develop a technique for doing that. And that's where section 4.4 comes into play. We have a new definition. The convolution of two functions. So remember, right before break, somebody said, boy, this class is getting convoluted. And I said, not yet. Very soon. Convolution. The convolution, f star g, of two piecewise continuous functions is defined by f star g at t is the integral from 0 to t of f of tau g of t minus tau d tau. Now I have a very difficult time writing and telling my t's apart from my taus. So I'm going to use a different letter. I'm going to use my favorite letter. I'm going to use x. So I'm going to use this as the integral from 0 to t of f of x g of t minus x dx. That's the definition I'm going to use. Okay, so we'll come back to this in a minute. Let's do some convoluting. Oops. Let's pick two relatively simple functions. F of t is the function sine t, and g of t is the function 1. And I want to find f star g.
Is this like kind of like compositions, like f equals g almost?
Sort of same idea, but not really. That's why we use this new symbol. We don't use the composition symbol or the standard multiply symbol. But you're along the same lines. We're starting with two functions. We're doing something with them, and we'll get a new function. And that's what happens with compositions. You start with two functions, you do something, you get a new function. In mathematics, we call those operators. So composition is an operator. Convolution is an operator. An operator means you start with two functions, you do something, you get a new function. All right, well, according to our definition, this would be the integral from 0 to t of f of x times g of t minus x dx. So that's the integral from 0 to t. What's f of x? Sine of x. Times, what's g of t minus x? Function 1, because g is the function 1. So I picked this function for a reason. Why did I pick this function? Because it's really easy. All I can do is multiply by 1 dx. So this is a very easy convolution to do. The integral of sine x is negative cosine x. Evaluate at 0 and t. So that's negative cosine t minus 1. So there's the convolution of sine t and 1. That's it. That would be my answer. If I asked you to compute the convolution, that's all you would do.
So could you do this with the really complicated problems you had and stuff?
So you want a harder problem? All right.
That's all here.
F of t is, we'll stick with sine t. Sine t was okay. Give me a function for g of t, which is more complicated than just the number 1.
Hyperbolic cosine.
Can we do like 3t, or is that?
Yeah, let's not go too crazy to begin with. Let's go with 3t. I like 3t. 80 steps, that's right. All right, so this time f star g would be the integral from 0 to t of f of x. F of x is still sine x times g at t minus x. That's going to be 3 times t minus x dx.
So why didn't you write for first 1 minus x? For g of 1?
If g of t is 1, what's g at 5? What's g at negative 3? What's g at a million? What's g at t minus x? 1. It's always the number 1. It doesn't matter what number, what letter I plug in. G at t is always the number 1. So that's why I used 1 there. This time, unfortunately, I have a t. So when I want to find g at t minus x, wherever I see a t, I have to replace it with a t minus x. All right, well, a little algebra here. This is the integral from 0 to t of 3t sine x dx minus the integral from 0 to t of 3x sine x dx. What did I do? I distributed the 3 through, and then I split it, right? I distributed the sine through also, so I had 3t sine x minus 3x sine x. Oops, that's a t right there, not a 3.
So you distributed the 3 through, so 3t.
Technically, I distributed the 3 sine x through. So I have 3 sine x times t.
Oh, okay.
That's 3t sine x. And I have 3 sine x times negative x. There's that. What's the antiderivative of 3t sine x dx? Negative 3t cosine x, evaluated at 0 and t. Minus, what's the antiderivative of 3x sine x dx? That's an integration by parts problem. That's correct.
Oh, you can use tabular method, right?
I can use tabular method. In fact, I'm going to use tabular method. I like tabular method. So I'm going to have my u and my dv. What should u be?
3x.
3x. The derivative of 3x is 3. The second derivative is 0. Here I have sine x for my dv. The integral of sine x. Negative cosine x. The integral of negative cosine x. Negative sine x. All right, so there's my minus that I had before. And then for this tabular method, we multiply this way. So that's minus 3x cosine x. And then the next one gets a minus. And you multiply this way, it's got another minus, so that's going to make it a plus 3 sine x. And again, I got to evaluate at 0 and t. Alright, so I plug t in. When I plug t in, I'm going to have negative 3t cosine t minus, when I plug in 0, I'm going to have negative 3t, so it's going to be plus 3t. So I plugged t and 0 into the first piece. Minus, I plug in t, I get negative 3t cosine t plus 3 sine t minus, when I plug in 0, that works out really well because I get 0 there, that one's 0. Sine of 0 is 0, so when I plug in 0 there, I just get 0. It looks like my final answer is, combining like terms, 3t minus 3 sine t. Questions on that one? How do they get harder? They don't. That's as hard as they get.
Wait, really?
No. If the teacher wanted to be mean,
Which George?
You do 2 parts.
how would he make it harder?
Like a repeating parts problem?
Okay, so instead of using 3t, I could use 3t squared.
Yeah.
But that wouldn't be too bad. You could still use the tabular method.
Well, no, I mean, like, repeating meaning like it's cyclical, like it.
Oh, so if you were saying, like, if I use sine t and then e to the t. Yeah, those would be harder. Those would be those ones that cycle around on each other. Yeah, those would be harder. I agree. What's that?
That's not good.
That's not too bad. What if, oh, I got to get them in the right order here. What if I let f of t be cosine t, and g of t be sine t? Well, f star g would be the integral from 0 to t of cosine x sine of t minus x dx. How do you integrate that? Well, I can't distribute. Sine is a function. I'm not multiplying there. That's sine of t minus x. Integration by parts? Kind of. What would you let u be? Cosine x, and so dv would be sine of t minus x, and what's going to happen?
It's not going to work out.
Well, when you take the derivative, you're going to get a cosine. When you take the integral, you're going to get a sine. So all that's going to happen is you're going to switch this one from a cosine to a sine. You're going to switch that one from a sine to a cosine. And then you do it again, and it cycles around on itself, because when you take the derivative twice, you'll come back to a sine. When you take the integral twice, you'll come back to a sine. So you could integrate by parts. That would work. Anybody got a better way?
I don't want to do trig integration, but maybe.
You're close. This isn't one we do very often in Calc 2.
Trig substitution.
Not trig substitution, no.
Oh, I remember.
We're going to use one of our favorite trig formulas called product to sum. Why will that help? It breaks it up. Instead of having multiplication, we're starting with a product. We're going to write it as a sum, and integrals are very good with summations. They're very bad with multiplication. All right, so here's the formula. I had to look it up. I didn't know it, to be truthful.
I make me feel better because I don't know.
I mean, I knew it existed. I just didn't remember exactly what it was. Cosine of A times sine of B is 1/2 sine of A plus B minus sine of A minus B.
So should this be something on our note cards then?
Now, this isn't one you
Okay.
need to have memorized for use.
This is
All right, so this becomes the integral from 0 to t. 1/2, I'm going to take the 1/2 and I'm going to put it all the way out front. Sine of A plus B. In this case, A is x and B is t minus x. So I add those together. What's x plus t minus x? T. So that's sine t. Minus, what's x minus t minus x? What's that? I get it the other way around. It should be x minus t minus x. So that turns out to be 2x minus t. So that's sine of 2x minus t dt. That's 1/2. Oops. The x down there, dx. What's the antiderivative of sine t dx? X sine t. Because sine t, when you have a dx, sine t is a constant. That's just a number. So the antiderivative of sine t dx is x sine t minus, what's the antiderivative of sine 2x minus t? 1/2 negative cosine 2x minus t. How'd you get that? It's a u substitution. You let u be 2x minus t. So du is 2 dx. So the 2, that's what brought the 1/2. The antiderivative of sine is negative cosine. And then you plug your u back in. Evaluate at 0 and t.
I need a sine t for sine t.
This one?
Yeah.
This one came from sine of a plus b. So I had x plus t minus x. X plus negative x. Those reduce out. There's just a t left there. Okay, so this is 1/2 times. I plug t in. When I plug t in, I get t sine t plus 1/2 cosine t, because I'm going to have 2t minus t, that's just t, minus, I plug 0 in. When I plug 0 in, I get 0 right there. 1/2 cosine of negative t right, because I'm plugging 0 in for x. So I'm going to have 2 times 0 minus t, that's negative t.
I'm trying to put it. Oh, I see it. I was trying to read the T part.
So final answer is 1/2 t sine t. Because what's cosine of negative t? What does cosine do to negative things? It eliminates them. So cosine of negative t is the same as cosine t. So I've got a 1/2 cosine t minus 1/2 cosine t. Those cancel out. Questions on that? All right, so back to convolution. Commutative property of convolution. A convolution happens to be a commutative operator. F star G is the same as G star F. Are all operators commutative? No, give me an example of one that isn't. Division usually isn't considered an operator because it doesn't deal with functions, it deals with numbers. 5 divided by 2 is not the same as 2 divided by 5. I agree. Composition is not commutative. F composed with G is not the same as G composed with F, usually. But it does work for convolution. I'm going to prove this one because it's fairly easy to do. F star G, by definition, is the integral from 0 to t of f of x, g of t minus x dx. And I'm going to take that and I'm going to do a u substitution. I'm going to let u be t minus x. If u is t minus x, what's du? Negative 1 dx. So this becomes the integral. When I get all done, I'm going to have du here. So I can't have f of x. I've got to have the letter u here. What's x? Come back here and solve this equation. You get x is t minus u. So that's f of t minus u, g of u, because t minus x is u, du. What are our bounds of integration? Nope. I got to put them in terms of u. If x is 0, what's u? T. And when x is t, u is 0. And then I made one small mistake. I forgot my negative, didn't I? My du is negative dx. So I need a negative 1 right here. So now what? Well, no, I'm not even going to integrate. What does this negative sign do to these bounds of integration? It flips them. So that becomes the integral from 0 to t, f of t minus u, g of u du. So notice what we've done. We started with g of t minus x, now we have f of t minus u. We started with f of x, now we have g of u.
Oh, spun around.
We've spun them around. So what do we have now? We have g star f. All right, so you might have noticed that when I wrote these, I very carefully chose g of t to be the function 1. Why did I very carefully choose g of t to be the function 1? Because when I went g of t minus x, I wanted to have just 1. What if I'd have flipped these around? What if I had to let f of t be 1 and g of t be sine t? Then we would have had a 1 here, and we would have needed to write sine of t minus x, which seems to make the integration harder. But you don't have to do that. If I had given it that way to begin with, you could have just said, well, I'm going to flip the two functions to make it easier. So same thing down here.
So whichever one's like easiest, we can just flip it. Or if it's hard, we can just flip it.
So the general idea is whichever function is the easier of the two,
Make that the G.
you want to call that the g of t one. It'll make your integration easier. Okay? Unless I give you sine and cosine, in which case they're equally crazy, so it doesn't matter which one is which. You work it out. equally crazy. All right, here comes the big theorem. Suppose f and g are piecewise continuous and of exponential order. What did that mean again? What did piecewise continuous mean?
I mean, it's like curves, right? They connect.
No, don't necessarily connect.
They're just curves, no connected.
You've got chunks of continuous,
Yeah.
but you only have finitely many discontinuities. So piecewise continuous might have looked like this. But there are only finitely many discontinuities. So you have a function that's each piece is continuous, and there's only finitely many discontinuities. That's what piecewise continuous meant. How about exponential order? What did that mean again?
Increases faster than an exponential function.
Increases slower than an exponential function. Increases slower than an exponential function. So if f and g are both piecewise continuous and of exponential order, then the Laplace transform of f convoluted with g is equal to the Laplace transform of f times the Laplace transform of g. Or conversely, the inverse Laplace transform of capital F times capital G is little f convoluted with little g.
So if you ever get that, like, if you ever get a inverse Laplace transform like that, it's convolution.
That's exactly right. The moral of the story is, I don't know about don't lose hope.
When we get that, we just do convolution, right?
The moral of the story is absolutely. When we get to this, we had an option of doing partial fractions, but we saw partial fractions with repeated quadratics was usually a pain in the neck. Another option is we can split it this way and convolute. So x of t is cosine of t convoluted with sine of t. So you kind of have to pick your poison. Which one's easier? Is it easier to do the partial fractions? Or is it easier to do this convolution, which we saw a few minutes ago involved an integral?
It must depend on what the situation is.
I agree. It depends on the situation.
Well, that one isn't the easiest to convolute.
This one's not the easiest to convolute, but I still think that this convolution is probably easier than doing the partial fractions.
This stuff, I don't know. So she's giving us tools to use this, but yeah, help us learn when to use it.
Yeah.
That's the challenge, I guess.
So what did we end up with an answer? 1/2 t sine of t, I think was our answer.
It's funny how like so much work just into a tiny little answer.
Yeah.
Math is not sure,
Right, because that's the problem we just did, remember?
Yeah.
That's why I picked that one. That's why I picked convolution of cosine t and sine t, because I wanted to be able to answer that problem. Questions on that? All right, so you're going to have some homework problems that look like this. Find the homework problems here. Determine the inverse Laplace transform of 1 over s times s squared plus 4. This is number 8, in case you're wondering. Well, what you might notice is you could write this as 1 over s and 1 over s squared plus 4. What's the inverse Laplace transform of 1 over s?
Where?
1.
Get one over there.
The inverse Laplace transform of 1 over s is 1. Convoluted with, what's the inverse Laplace transform of 1 over s squared plus 4?
Sine of
1/2
sine
sine of 2t. Because it's got a 4 on bottom, you really need to have a 2 on top to match the inverse Laplace transform form, which means you need a 1/2. So 1/2 sine of 2t.
So we can make the 1 the G, right?
So you can make the 1 the g, which means you need to take the integral from 0 to t of 1/2 sine of 2x times, and the beauty of having 1 there is it's just 1 dx. So what's the antiderivative of 1/2 sine of 2x? Negative 1/4 cosine of 2x. Evaluate at 0 and t. So that's negative 1/4 cosine 2t plus 1/4. So again, the question is doing that convolution, having to work out that integral, easier than having to do the partial fractions?
Yes. Extremely.
I think for this one, that was easier, definitely.
On the test, we just do a bunch of convolutions.
On the test, I will ask you to find the inverse Laplace transform. I don't care which way you do it.
Okay.
You can use partial fractions or you can use the convolution. Max.
So, a weird question. What's the history of this? Like, who is this Laplace guy? Like, and I'm being serious, because where did this come from? I mean, I know Newton did calculus and stuff like that. Yeah.
All right, how about the inverse Laplace transform of 1 over s squared times 1 over s squared plus 9? This is similar to number 10. In problem number 10, they didn't give you a number 9, though. They just left that as k squared. I decided to make it slightly easier and use a number instead. Again, you could decide to do the partial fractions. You would need an a over s, a b over s squared, a cs plus d over s squared plus 9. Or you can choose to do convolution.
I think this seems less convoluted.
It seems less convoluted.
Yeah.
Anti-convolution, this should be called. All right. What's the inverse Laplace transform of 1 over s squared? D. Convoluted. What's the inverse Laplace transform of 1 over s squared plus 9?
1/3 sine.
Same deal. You really need a 3 on top. So you need a 1/3. So it's 1/3 sine 3t. So when I do my convolution, I'm actually going to switch it. I'm going to have g be t. So this is going to be the integral from 0 to t of 1/3 sine 3x times t minus x dx. That's the integral from 0 to t. 1/3 t sine 3x dx minus the integral from 0 to t of 1/3 sine 3x times x dx. The first one is very easy to integrate. What's the antiderivative of 1/3 t times sine 3x dx?
T sine 3x. Oh no.
So is this when we actually treat the T as another number?
The t is a number. That's absolutely correct.
Just kind of ignore
So-
1/9 sine.
So you're going to have 1/9 negative. All right, so it's going to be negative 1/9 t cosine 3x evaluated from 0 to t. Minus, what are you going to do with this one?
Parts.
Integrate by parts. But again, integrating by parts using that tabular method to me is pretty quick and pretty easy. So again, I'm going to use parts. U and dv. U is x. Derivative is 1. Second derivative is 0. dv is 1/3 sine 3x. Integrate once, I get negative 1/9 cosine 3x. Integrate again, I get negative 1/27 sine 3x. So I have, multiplying that way, negative 1/9 x cosine 3x, and then minus, and I multiply this way. That one's got a minus, but it's got another minus here, so that's going to make it a plus 1/27 sine 3x. Evaluate at 0 t. Alright, so all that's left to do is plug in my numbers. I have negative 1/9 t cosine t plus 1/9 t, because when I plug in 0, cosine of 0 is 1.
Cosine of 3.
Cosine of 3t, thank you. Sneak the 3 in there. Minus, when I plug in t, I'm going to have minus 1/9 t cosine 3t plus 1/27 sine 3t. And then when I plug in 0, I'm going to have 0 right there, so that whole term is going to be 0. Sine of 0 is 0, so that'll be 0. Final answer looks like, when I distribute this minus through, this minus 1/9 t cosine 3t and a positive 1/9 t cosine 3t, those go away. Only thing left is a 1/9 t plus 1/27 sine 3t. What's that? Sure, minus 1/27. So again, you have to make the decision, which is better, partial fractions or convoluting. We have to do an integral, you end up having to do a little integration by parts. Your decision.